Last time we started looking at prime and composite numbers. And we had done 3 examples, basically all kind of revolving around how to factor. The first one was an example where it was just the number was there, we factored it from its most, expanded, if you will, form, and we had to break it down into all its smallest pieces. This one had it sort of broken down, but only partially, and we had to finish breaking it down and organize it a little bit. And this one had components that were broken down and organized, but then they added 2 of these together, so we did some factoring out of like terms and simplifying. So I'd like to continue with a few other things in this section. The first one is called the fundamental theorem of arithmetic. So any time in math that they put the words fundamental theorem on them, it means it's pretty important, all right? So this says each composite number can be written as a product of primes in one and only one way if you don't count the order, right? So like 6 is technically 2 times 3 and 3 times 2. We don't count those as different things, okay? So the order doesn't matter, but there's only one breakdown of primes that you can take any number down into. And in particular, that's actually at least one of the reasons why we wouldn't want the number 1 to be considered a prime number. Because we'll just take a real simple example, number 6. Number 6 can be written as 2 times 3. But if 1 were a prime number, it could also be written as 1 times 2 times 3. But it gets worse because it also could be then written as 1 squared times 2 times 3. Or 1 cubed times 2 times 3. Right? But hopefully you're looking at that and going, yeah, but 1 to the any power is 1, so what's the point? And that is kind of the point, is that it doesn't add any value to what you're doing. So we do not have the number 1 as a prime number. And because we don't, we do have this fundamental theorem of arithmetic that says there's only one way to break down a number into primes. Another theorem, if D is a divisor of N, then N divided by D is a divisor of N. What this really says is that divisors come in pairs. So let me give you an example. Let's say that we're looking at the number 24. And we know that 3 divides 24, and it does, right? Then if you took 24 divided by 3, which we know it exists, you would get 8, and 8 would also divide 24. So these numbers that divide whatever value we're looking at come in pairs. And if we think about it that way, it usually saves us time on finding all the divisors if that's a question we're asked. Because if I find out that 2 is a divisor, then 2 times whatever it was is also a divisor. 3 times whatever is also a divisor, and so forth. Now, one of the things that happens at some point is you're given a number and you're asked, is it prime or composite? And especially if it's not even, you might be left going, well, I'm not really sure. It's big enough. I don't really know for sure. I think it might be prime, but I don't know. And how many numbers do I have to test to know for sure? Are you with me? Because, I mean, if the number is not divisible by anything until I get to, like, 31, that's quite a few numbers I have to test till I get to 31. And when do I know that I can stop? I mean, if it isn't divisible by 31, do I have to keep going? I mean, how far is far enough? And that's actually what Theorem 415 says. It says that if you have a composite number, and it does have a factor, then that factor is less than or equal to the square root of the number. And they write it a little bit differently, but this is actually what I said. The factor is less than or equal to the square root of that number. And if that doesn't happen, that's what 416 says, then it's prime. So, all I really need to do in terms of knowing when to stop is to take the square root of what I'm looking at. So we have a pretty big number kind of example next. The number is 967. And unfortunately, it's not got a 2 or a 4 or something like that on the end. So I know it's not even, but that doesn't mean I know for sure whether it's prime or composite. So we're going to take the square root of 967. And with 1 decimal is fine. What is that approximately? Anybody have their calculator out? Tell me what that approximates to. Okay, 31.1. And folks, that's good news because the number 31 is way smaller than the number 967, right? So what does this mean? Well, it tells you that once you hit 31, if it's not been divisible by anything before then, it's not going to be divisible by anything. So the question exactly that it asks is, what is the greatest prime number you have to test? I haven't actually answered that question yet, but what is the greatest prime number that you would have to test? I mean, 31, right? 31's the biggest prime number underneath this value. 31. Now, if I happen to be testing them and I get to 17 and 17 works, that's great. I don't have to keep going, right? And I know. But if I get to 31 and all the numbers I've tested so far up to 31 didn't work, I don't need to keep testing because nothing will. Does that make sense? All right. I already did this example. I didn't remember I did it, but we'll do it out with the number. It says, show that if 1 were considered a prime number, every number would have more than 1 prime factorization. This is what happens when you've taught something multiple times. You forget that it was already in there. We did this for the number 6. I talked about the fact that 6 is equal to 2 times 3. And if 1 were prime, we'd have to write also 1 times 2 times 3. Or 1 times squared times 2 times 3, and so forth. Yeah, that's not cool. Not cool at all. All right, let's do an application. Mr. Arbor wants to plant apple trees in a rectangular array. If he has 36 saplings, find all possible numbers of rows if each row is to have the same number of trees. So, we don't want uneven rows. Makes sense. How many rows could I have if I were Mr. Arbor? Can somebody give me a possibility? What was that? I could have 1 row of 36 trees. So I could also have 36 rows, right? So 1 and 36 are possibilities here. It'd be a really long row of trees, but yeah, why not? What else? I could have 2 and 18, right? They're occurring in pairs. I did a theorem about this, right? If we keep track of them, we have to do half the amount of work. What else could I have? I could have 3 or 12. What else? 4 or 9. 6. And if you want to write the pair for it, 6, I'm not going to fuss. And 6 rows of 6 trees, right? 6. Yeah. These are all the different numbers of rows I could have with each row having the same number of trees. Because I'm looking for divisors of the number 36. All right, Bob is our last example today. Bob says that to check whether a number is prime, he just uses divisibility rules that he knows for 2, 3, 4, 5, 6, 8, 10. He says if a number is not divisible by these the numbers, then it's prime. How do you respond? Okay, so 91 is 7 times 13. And it's not prime, but also won't divide by Bob's list. examples are really good. It's one thing to argue why something doesn't work, and that's fine, but showing an exact example where it doesn't work is often a lot more clear. So I think this is a really good way of thinking about this. After showing Bob this, it might actually also be worth talking to him about the fact that he's duplicating things that don't need to be duplicated, right? For example, if he's already divided by 2, why is he dividing by 4, 6, 8, or 10? You know what I'm saying? If 2 doesn't work, 4, 6, 8, and 10 are not going to work either. There's no reason to test them. So he's actually doing more work in some cases than he's even needed to do to test. And he's missing things, which is what Brooke said. Basically, he's missed something along the way. In fact, a really small number that would be a good example as well that he probably would know at this point would be like the number 49, right? As 7 times 7, because you know multiplication tables for 7 times 7, right? Or 77, 7 times 11 is also in our multiplication table list. So there's lots and lots of examples we could give Bob to show that that's going to fail in some cases.